I'm just choosing P to be the
base point. Yeah.
Then Q minus P, or the vector from P to Q,
Okay.
is the A vector.
Uh-huh.
And then the vector from P to R is the E vector.
Okay. Very good. I think that should do it. And if we put that down here, that would give us what? R of ST equals, you said R naught was P, right? Plus S times A vector is PQ, which is Q minus P, is it not? Yeah. There's a typo in the notes about that. You found? Which page was that?
13.
13 typo. I'll fix that sometime soon. I've got P minus Q where I meant to put Q minus P or vice versa. But and then TB vector is R minus P. That is the parameterization of a plane containing those 3 points. And see how it works? R of 0, 0 is what? It's P. What's R of 1, 0 equal to? Q, okay. And what's R of 0, 1? And what's R of 1, 1? I think it's P plus Q plus R, right? Yeah. So look, what's going on here, and I'm sorry, I seem to have jumped the ship on my color coding with A and B, going from one picture to the other. These things happen. But, okay, so where's X, Y, Z in this? There is no explicit X, Y, and Z, right? This is a parameterization of the plane. So, in some sense, what it's doing is it's setting up S and T as coordinates on the plane. So there's like S coordinate lines and T coordinate lines, right? So like in this picture, if S varies, it would be, I mean, let me just mess up my picture, but basically you've got lines like this, right? These lines on the plane are lines where what? These have T fixed. S varies. Those are S coordinate lines, like the x-axis, you know? And on the flip side, following B, you've got these ones, right? And these have S fixed and T varies. And that's what we're doing with the parameterization. We're laying down a grid of coordinates on the plane. And like, we don't care about X, Y, and Z so much anymore. Now we've got S and T, and that's enough because that leaves us in the context of the plane, yeah.
And A and B don't have to be perpendicular, right?
No, they do not. So it could be a kind of like slant coordinate. But they can't be collinear because then it's not a plane, it's a line, yeah.
Can this method be used to determine where a line is in regular 3D space or just in relation to the plane?
Can this method be used to, say your question again while I'm erasing here.
Can it be used to determine the direction of a line like a vector in a regular 3D plane, or is it just in relation to the plane in a sense?
I don't understand the question yet, I'm sorry, but like we can use this approach or this approach on a given plane. It's possible to go from one, we can always go from this point, this viewpoint to that viewpoint and vice versa. Sometimes it's possible to use X and Y as parameters on the plane, right? Like that's also conceivable, like over here. If I wanted the parameterization of this plane, example 3, I don't know if you guys remember, how much you guys remember about like your work in parametric stuff last semester or whenever you took this, but a lot of that kind of ad hoc algebra stuff you did, a lot of that's still possible, you know, like solving for a variable or something. Like here, if I solve for z, I have z equals to what? Minus 3 times x plus 10 plus 7 times y minus 3, right? All divided by what? 13, right? So check this out. R of x comma y equal to x comma y comma, 1/13 of, minus 3 times x plus 10 plus 7 times y minus 3. Lo and behold, this is a parameterization of the plane in example 3, where I'm using x and y as parameters. This is kind of a halfway house between the equation idea and the parameterization idea, right? Because I'm using Cartesian coordinates as parameters, and that is at times convenient. So this right here is what we call a graph. When we say z equals to a function of x and y, so this right here is a function of x and y. F of x, y is our notation typically in here. So we can, of course, write a plane, not of course, we can sometimes write a plane as a graph of a function in x and y, but not always, yeah. The parametric viewpoint is totally general, and this equation is also totally general, all right? Anyway, yes?
So when we plug in our parameters s and t, that gives us a point within it. Not a point, I'm sorry.
Yeah, it gives us a point,
It gives us a point.
a specific point on the plane, yeah.
And that, is that and the same x hat, y hat, z hat? If it's okay, that point.
Wait, why are we talking about x hat, y hat?
Well, I'm saying, I guess, does it, when you get the point.
The parameterization is giving us a point on the plane.
Yep.
That point corresponds to a vector based at the origin out to that point.
Okay, yes, that
Yeah. Now, if the base point happens to be the origin, then things kind of collapse down a bit, right? But, okay, so now that we have these toys, we'd like to play with them and solve problems that involve lines and planes, right? And so, like, one of the things we can think about is how on earth would you describe a line with equations? We could do that. I think I'll save that for next time because that's kind of weird. So let's see here. How about this? Example, what am I on? I guess 4. So let's suppose we have a plane and it contains the points 1, 2, 3, 8, my bad, 1, minus 1, 8, and also I'll throw another point over here, let's say minus 3, 5, 0, all right? So we got a plane, it contains these 3 points. You guys with me? Suppose we have a point off the plane. Oh. I'll call that point let's just go with 6, 7, 6. So then I can ask the question, what point on the plane is closest? Can you find the closest point on the plane to that point off the plane? So let me tell you how we're going to do this. We need to find the normal, and then we need to find the normal line. And then we need to find where that normal line that goes through the point off the plane intersects the plane. So the things we need to do to solve this problem are to first find the equation of the plane. In so doing, we'll find the normal line. We'll find the equation, we'll find the normal. Then we have to write down the equation for the normal line, right? And then step 3, we'll plug the equations for the normal line into the equation for the plane, and that will give us the parameter for the normal line that shows us where we intersect the plane. I may or may not get through all of that in class today. So, because first of all, we have to figure out, what's the equation of plane. So we need to figure out tangent vectors, don't we? So I'm going to call this A. I'm going to call this one over here B. So A is equal to, A is equal to, what we got? 1 minus 1, 0. B, minus 1 minus 2 is minus 3. 8 minus 3, 5. That's my one displacement vector, which is a tangent vector to the plane. The B vector, minus 3 minus 1 is minus 4. 5 minus 2 is 3. 0 minus 3 is minus 3. I need to find the normal vector. This is going to hurt a bit, but not too much. It's just, we do have to do the cross product, right? So A cross B. Let's see here, 9 minus 15. Let's see here, minus 20. Minus 12, I think. So I got cross product of minus 6, minus 20, minus 12. Before I go on and do anything else, I check if my cross product is perpendicular. Right? This is something you must do on the test. You must take a second to check your cross product is correct. Do not just do it and not check it. This is a foolish thing to waste points on. Because everybody here can do the cross product, but you have to be careful. There's so many opportunities for arithmetic mistakes. After this speech, if I have an error here, I have mixed feelings. But 0, 60, minus 60, hooray. Dot product of this and that. So 24. Minus 60, minus 36, plus 36, yep. So it's perpendicular to both, that's a good sign. What's the equation for the plane then? We can use, you got your choice of base points, right? Which one do you guys want to use? It doesn't matter. 1, 2, 3, all right, fine, we'll do that. So minus 6 times x minus 1, minus 20 times y minus 2, minus 12 times z minus 3. There you go, guys. That is the equation of the plane. And sometimes I just ask you that equation. I say, here's 3 points on a plane, find its equation. Yes, sir? So this is the normal. All right. So I'm saying it's geometrically clear that the line which is the line which has direction of the normal vector goes through the point on the plane which is closest. So I'm thinking about this line here, right? So what's this point of intersection? I need to find that. So I need to write down the parameterization of that line, that normal line. So I'll do the easy part. T times the normal vector Now you say, well, your picture might be wrong. Maybe that point's below the plane. So your normal vector should be replaced with minus. It doesn't matter. You'll get t as negative or positive. It doesn't. It cover all math covers all contingencies here. What should I use as the base point on this line?
6, 7.
I can't use 1, 2, 3. That is not true. What's that?
Would it be the 6, 7, 6?
You said 6, 7, so we'll go with that. Let's see here. 6, 7. I feel like this feels like a trap. Let's see here. 6, 7, 6 plus t. So yeah, we have to use that because that's the point we know is on the line, right? Now, what does this mean? This means that on the line, we have parametric equations, x equals 6 minus 6t, y is equal to 7 minus 20t, and z is equal to 6 minus 12t. So all you got to do is you take these equations and shove them up here into this equation. That gives you one equation and one unknown for time. You solve those equations, it gives you the time that the normal line intersects the plane. You take that time and you plug it into the parameterization, you got the closest point. That's how you do it. I think this is actually a little bit easier than the projection problem we did for the closest point on the line with the projection stuff. I don't know why, it feels easier to me. But then again, I'm used to this. It may feel not so easy to you at the moment. That's fine. One day at a time. Thanks, guys. So, see you tomorrow.